Hi there. In this video, we're going to be looking at rates of change of multivariable functions. When we speak about rates of change, we're speaking about time. We're asking, how does something change with time? We saw in the last video that some multivariable function, or rather a change in some multivariable function, that would be delta z, is equal to dz dx multiplied by delta x, some change in x, plus dz dy multiplied by some change in y, delta y. So if I divide this entire equation by delta t, I would get delta z divided by delta t is equal to dz dx times delta x divided by delta t plus dz dy times delta y divided by delta t. If I then let delta t approach 0, what I'm going to get is that dz dt will approach dz dt. So dz dt is equal to dz dx times dx dt plus dz dy times dy dt. What does this equation mean? What this equation means is that if I have some variable z, which is a function of x and y, and if I want to understand how does this variable change with time, well, I would say that it's equal to the rate of change of z with respect to x multiplied by how x changes with time plus the rate of change of z with respect to y multiplied by how y changes with time. So if we were to look at an example, and this example could be a cone. We have a cone. The cone has some radius. There's the center, the base of the cone, and it has some radius, and it has some kind of height. So this has a volume, okay? It has a volume. And the question would be, how is the volume changing if we were to change one of these variables? Let's just say, for example, the radius is changing. The radius is getting bigger. If the radius is getting bigger, then of course the height is getting smaller. So the question is, how is the volume changing in that instance? In the scenario that the radius is changing, the height is also changing, how is the volume changing? So we would need a relation between the volume and the radius and the height. So in this multivariable function, we would say that the volume is equal to 1 over 3 multiplied by pi r squared times height. This is the formula for the volume of a cone. It depends on two variables, the radius and the height. So we ask ourselves the question, how is the volume changing with time? And if we look at the result that we just derived, in that the rate of change of z with respect to t is equal to everything that you see on the right-hand side. What this means is that we can write the rate of change of volume with time to firstly be how volume changes with the radius multiplied by how the radius is changing with time. This is the first part of this equation, which is what you see here, dz dx, dx dt, that's dv dr, dr dt. And then the second part of the equation is how the volume is changing with the height, multiplied by how the height is changing with time. So we can now perform the derivatives on this equation. So dv dr is just simply equal to just 2r. Of course, we keep the height constants when we taking this derivative. So we get 2 pi r h divided by 3, and day v day h is just simply equal to pi r squared over 3 because the derivative of h is just 1. Substituting all of this inside this equation, we get day v day t is equal to day v day r, which is 2 pi r h over 3 multiplied by dr dt plus pi r squared divided by 3 times dh dt. So if we were to just take some numerical values, okay? So let's just say we had the rate at which the radius was changing, and also we had the rate at which the height was changing. So let's assume that the radius is changing at a rate of something like 1.5 millimeters per second. So dr dt, so the radius is changing at 1.5 millimeters per second, and the height is changing at a rate of perhaps 6 millimeters per second. So this is getting bigger and bigger, the radius is getting bigger, and the height is getting smaller at a different rate. So we can substitute these values in, and we can actually calculate at a specific point. So at a particular radius and a particular height, given that it's changing at a specific rate, what is the rate of change of volume at a given point? Let's just say, for example, at a radius of 12 millimeters and a height of 24 millimeters. What is the rate of change of volume at this specific point? Well, we can substitute all our values in. So day v day t is equal to 2 pi 12 multiplied by 24 divided by 3. All this multiplied by dr dt, which we saw to be 1.5. And we would add to this pi r squared. Again, r is 12. Square that. Divide this by 3. And our height is decreasing. And we saw that height to be -6. Sorry, this is a -6 here. So as the radius is getting bigger, the height is getting smaller. We can imagine this practically. If we have a cone and we can adjust the size of the cone and be able to pull the radius outward, make it bigger, we can see that the height would get smaller. Think of a tent or something like that. That would be -6. So substituting these values in and performing the calculation can easily compute this. You see that it's 288 pi and -6 times 12 squared divided by 3 times pi. That also gives you 288 pi, which is just 0. So what are we saying? What does this result mean? It means that for this cone, with its radius changing, coming outward, height going down, at a specific value, r is equal to 12, h is equal to 24, there is no change in the volume. The rate of change of volume with time is equal to 0. The amount of whatever it can hold, this cone, what can be put inside it, will not change if the radius is changing at this rate corresponding with that change in height. So this is an example of how we have a multivariable function, the volume, depending on the radius and the height. We're looking at it at how it's changing with time, if the radius and the height are changing, and and we computed it at a specific point. We specified how the radius is changing with time, we specified how the height is changing with time, and we looked at a specific point that was r is equal to 12 and h is equal to 24, and we looked at what is the rate of change of volume at that point, and we discovered there is no change in volume at that point.